Hello and welcome to my presentation about deep interference mitigation and denoising of real-world FMCW radar signals. Automotive radar is used for driver assistance systems and autonomous driving. In both applications, environment perception is the task, so we are interested in the range, the velocity and the angle of objects that are within the environment of the radar sensor. In automotive radar, typically the frequency-modulated continuous wave chirp sequence radar is used. And we face the challenge of mutual interference, where multiple radar sensors send with overlapping frequencies and thus introduce an interfering signal to other radar sensors. In this work, we evaluate CNN-based models for interference mitigation. To do so, we use real-world measurements and mix them with simulated interference. We give a comparison with the state of the art. But we are not only interested in the model performance, but we are also interested in certain hardware constraints, such as the model size, because in practice this also matters. First, I would like to give a short overview of the range Doppler processing chain. In the first step, we have the radar sensor itself. It sends out linearly modulated radio frequency chirps, which we also call ramps. The object reflections that are received by the antennas are mixed with the transmit signal, which gives us the intermediate frequency or IF signal. This signal contains the distances and the velocities of the objects within the environment of the radar sensor through the time delays and the rate of ramp-wise linear phase change. In the figure in the bottom, you can see in blue the transmit signal, in red the receive signal, and in yellow the resulting intermediate frequency signal. This is a simulated IF signal in time domain. In the next step, a discrete Fourier transform is performed over the n fast time samples for each of the m ramps. The result you can see in the figure here. We have a signal in frequency domain now, where we have peaks at the distances where we have objects in the scenario. In the next step, another DFT is performed over the m ramps for each of the n fast time samples. The result is a range Doppler map, where we have peaks at the velocities and the distances where we have objects in the scenario. The next step is an object detection step, where we try to find the peaks in the range Doppler map that actually correspond to real objects rather than noise or cluster. The next step is the angle estimation, where for each object that was found in the range Doppler map, another DFT is performed over several antennas. This gives us the angle or the relative position of each object to the radar. And then there might be some further processing steps, such as sensor fusion, object classification, or motion estimation. There are several reasons why mutual interference is gaining more importance. First, we do have a non-regulated spectrum, so radar sensors can send overlapping frequencies and thus introduce an interfering signal to other radar sensors. Also, they use a ever larger bandwidth for a more fine-grained range resolution. And with a rising number of circulating radar sensors on the streets, we do have a higher risk of getting interference. The most common form is the non-coherent interference. It introduces broadband disturbances. In the figure in the bottom, you can see in blue the frequency course of the victim radar, in red the frequency course of the interfering radar, and in yellow the resulting intermediate frequency interference that is generated right at the ramp crossings. This is a simulated signal in time domain, on the left side clean and on the right side with interference bursts. After the first DFT, we can see on the left side on the clean data that we can see the 4 lines that correspond to the distances of the 4 objects in the scenario. On the right side, we have several interfered ramps, which we can see in yellow. And Within these ramps, it gets already harder to detect the 4 objects. After the next DFT in the range Doppler map, we can see that the interfered data on the right side has a higher noise floor. And the noise is not only random, but it rather has some structure in it. And note that this structure really depends on the ramp crossings of ego radar and interfering radar. Classical interference mitigation is typically performed either on time domain IF signals or after the first DFT on the frequency domain signals. CNN-based interference mitigation, on the other hand, can additionally be applied to the data after the second DFT, thus on the range Doppler map itself. We then call this range Doppler denoising, and the results that are presented within this work are all done by range Doppler denoising, because in our case this just performs best. The CNN-based model that's used for the results in this work entirely consists of convolutional composite layer. Each of these convolution operations uses the so-called same padding, which means that the activation, the spatial dimension of the activation, before the convolution operation and after the convolution operation stays the same. Also, we use 3x3 kernel filters in each convolution operation. Also, we use batch normalization and the ReLU activation function. As inputs for the CNN, we use the measurements mixed with the simulated interference, and as targets or outputs, we use the measurements but without this interference. In both cases, for input and targets, we represent the real imaginary spectrogram of the range Doppler map as 2 channels in the CNN. Our data simulation consists of point objects only. The parameters are randomly sampled from a uniform distribution, which does not introduce any biases and thus makes it easy for our models to learn. Also, the interference is simulated, and it's added to the object reflection signal in time domain, together with some additive white Gaussian noise. This would be an example of the range Doppler map of simulated data, on the left clean and on the right side with interference. We took our data measurements in inner city traffic scenarios. We took around 850 measurements, where each measurement consists of 32 radar snapshots or range Doppler maps, each with 16 antennas. When we analyzed our measurements, we found that we have rather complex objects, so the object peaks are clustered that can be distributed over the distance and over the velocity. Also, we found some very strong biases in our data. First, we have the ego velocity. At the velocity bin of the negative ego velocity of the measurement vehicle, we have all the static objects in the scenario contained in the same velocity bin, which you can see over here. Also, we can see the equipment reflections over here. They are always with a very close distance and at a relative velocity of 0. Also, for the measurements, we use simulated interference. And as with the simulated data, it's added to the object reflection signal in time domain. But in this case, we don't need any additional noise, because the measurements already contain a lot of thermal noise. As performance measure, we use the signal to interference plus noise ratio. It's defined through the power at the object peaks divided by the power at the noise floor. In order to get the ground truth peak locations, we use the cell averaging CIFAR peak detector on our clean measurements. Now I would like to show you the relation between performance and model complexity. We evaluated models with 2 to 10 layers and 8 to 512 filter kernels. And in the plot we have the number of parameters on the x-axis and the SINR metric on the y-axis. And we can see that already very small models, which are the models in this corner of the plot, they already yield a very high SINR performance. So the smallest model trained and evaluated on real measurements, which is marked with a D over here, has only around 1000 parameters, which is very small in the context of deep convolutional neural networks. The letters C and D mark the smallest models for simulated and real data that surpass the clean measurement SINR. And A and B are the overall best performing models. Here we have the same results but grouped by the maximum number of filters and the number of convolutional layers. So we can say, as a rule of thumb, if we have a model that has 3 to 7 layers and 32 or more filter kernels, this yields in a very high SINR performance. We were also interested in the effect that the number of training set samples has on the training and the performance. So we trained the same model on subsets of the training set with different sizes. Each training subset was used 10 times, and we then plotted the mean and variance of these results. We did that for simulated and measurement data, but the evaluation was always done on measurements. With 500 training samples and more, we have a very high mean SINR, where we have a very low variance of SINR. If we have a smaller amount of training samples, the mean SINR decreases, while the variance of SINR increases, over here. When training on simulated data, we need much less samples than when training with real measurements. But also, if we have more measurements in the training set, we can see that with simulated data we never reach the SINR value as we would reach it when training on real measurements. Here we have a performance comparison with the state of the art. This plot shows the cumulative density function of the SINR metric. As comparison methods, we chose zeroing, IMAT, and ramp filtering. And for comparison, we also included the interfered and clean SINR values in light and dark gray. All three classical methods slightly improve the SINR values on samples with strong interference. For samples with less interference, they even worsen the SINR values on the other hand. But the CNN-based model increases the SINR independent of the level of interference of the samples. Also, it even increases the SINR in comparison to the clean SINR values, which means that it performs some additional denoising on the measurement data. Here we have an exemplary measurement range Doppler magnitude spectra. On the left side with interference, in the middle the measurement without interference, and on the right side after the CNN mitigation. After the CNN mitigation, the interference patterns are clearly removed and the noise floor is further suppressed. But we can also see that the object peaks are retained at the same location and with the same relative intensity. In this presentation we have seen how real measurements can be mixed with simulated interference in order to train and evaluate CNN-based interference mitigation models. These CNN-based interference mitigation models are very well suited for real-world measurements. And they even outperform the state of the art by magnitudes. We've also seen that already very small models yield a high performance of SINR. And training set sample size matters. It matters even more for training on real-world measurements. Thank you for your attention.